All right, when you're taking or looking at video lessons, there's a couple suggestions on how you can use them more effectively. How you have a pause feature, which is really important. So if there's too much text to read, or if I've gone too fast through a question, or any reason you're not understanding, feel free to pause it, rewind it, try it again. On key questions and things, I'll tell you to pause and just write down something or read something. That's a really important use or advantage you get with a video lesson. But let's get into the physics. So Unit 2, or our second big block of information, is going to be about forces. So by the end of this section, I'll be able to recognize the forces acting on an object and draw something called a free body diagram or a force diagram of those forces. So dynamics is the study of the causes of motion. So in its most basic sense, a force can be considered a push or a pull that acts on an object. Sometimes we can see those forces, sometimes we can't. So a rope tied to a wagon we can see, but gravity, for example, we feel it, but we can't actually see it. So I have a little picture down here of a ball with a force going to the right, and it's again just a vector representation, the same thing that we did in the motion unit. The unit of measure for forces is a Newton. Okay, so in the metric system, that's what we're going to be using. If you're using imperial, you'd use a pound, but we're going to use a Newton, and it is defined as 1 kilogram meter per second squared. And it's a derived unit, which means it's made up of other fundamental units. That's a really important concept. It's also really difficult, because it's so new, to make connections to how big a force of 1 Newton is, or 10 newtons, or 200. Like, it just doesn't register with us. So just keep in mind a small apple down here, about 100 grams, is about 1 Newton. And as we go through more examples and things, we'll start to get a bit of a feel on how big a Newton is in terms of our day-to-day life. Okay, the unit that we're sometimes a bit more familiar with is the pound, and it has a symbol of LB right here, and that dates back to something called the Roman Libra, and it quite literally is the measurement of grains. So a type of grain that you've harvested, that's how far back it goes, and that's where that system sort of comes from. It's a neat little story here. If you want to have a little read, just pause it and take a look. We'll carry on though. So to measure the force on an object, one tool we can use is a Newton spring scale. I'll try and show you a little video of how it works in action. So one side of the spring scale measures in grams or kilograms, and that's a mass unit, and the other measures newtons, which is a force unit. So we'll try and use that in class if we get back there in time. And otherwise, I'll put a little video up there. So I have used that spring scale to measure a couple of masses. So I hung the masses on the spring scale, and it registered or told me the force acting on those masses. So if we look at this, you might want to pause and just look at the data for a minute and then look at the graph. And we should see that that's quite clearly a linear relationship. So if I connect all these little dots to help you see it, there's my linear relationship. If I asked for the equation of the line, we would see this is direct variation. So we know this is going to be some form of y equals mx. So if I could find the slope of this object, that would be really helpful. I'm going to use my grade 9 techniques here of finding slope. So we have a difference of 0.5 kilograms and a difference of 5 newtons. So if I looked at the difference between those two, that is going from here to here on my graph. So this is a change of 5 newtons, and this is a change of 0.5 kilograms. Come on, pen. There we are. So my slope, if I was to do my slope here, it would be 5 divided by 0.5, and I would get 10 newtons per kilogram. Okay, so my equation, when I go to set this up, I have force along the y-axis, I have this 10, which is my slope, and I have mass, which is along the x-axis. So if we look at those units, I'm just going to bring those down. 10 newtons. I better give myself a little bit more room to work here. 10 newtons per 1 kilogram. If you scroll back up to the top, and you can see that the definition of a newton is a kilogram meter per second squared. So this is 10 kilogram meters per second squared divided by 1 kilogram. Those of you who can recognize the algebra here will be going, hey, those kilograms cancel. And you'll be like, well, wait a minute. 10 meters per second squared. I've seen a number really close to that before. I've seen this number, which was the acceleration due to gravity. And voila. So the force of gravity, here is the equation you just developed. Okay, so the force due to gravity is equal to mass times g, and g is just the acceleration due to gravity. Okay, we sometimes use 10 just to approximate. So a 70 kilogram wrestler has a gravitational weight. If we were approximating, we would say it's 700 newtons. If we want to be a little bit more specific, it would be 70 times 9.8, and we would have 686 newtons. Okay, and that's just plugging in all of the information into our little equation. Okay, so now down here a truck pulls up onto a weigh station, not weight, weigh station scale, and has a weight of 20,000 newtons. What is the mass of the truck? So we take our little equation and we fill in the missing information. So 20,000 is the force. We're looking for mass. I'm just going to put 10 in for g for now, just for quickness of calculation. Then if I divide both sides by 10, I can see that the mass of the vehicle was 2,000 kilograms. Sometimes we do have to move between newtons and pounds, so connecting the two, 1 pound of force is equal to 4.45 newtons. Okay, so we've done these types of conversions before. So if you have 200 pound person, this is very similar to what we did with our motion unit. I have a ratio of 1 pound, so I'm going to put the 1 pound on the bottom, 4.45 newtons on the top. The pounds cancel, and all I have to do to get my new converted unit is multiply 4.45 times 200, and I get 890 newtons. Okay, so a 200 pound person is about 900 newtons, just to give you some gauge. So there's one of our first connections for linking newtons to day-to-day life. What forces are acting on this book resting on the table, and what forces are acting on this book as I push it across the table? So if you want, you could pause it here and think about this for a minute. Okay, so hopefully you've had a chance to think about it. So when we're just looking at resting on the table, there's going to be some sort of force that has to hold it up, because there's some sort of force of gravity that wants to pull it down. Okay, if I try and push the book across the table, okay, come on, book, slide across the table. There we go. You're being difficult. There we are. Well, it's kind of moving. You get the idea. I have to apply some sort of force to the side of it to make it move. But what I usually feel anytime you push something across the table, the floor, wherever, there's usually some sort of force that opposes that. Okay, so what we want to do is we want to give some names to those things, and this would be a good page to pause on. So after you've had a chance to read those and write them down, I'll go over them really quickly. Applied force, which we call FA, is a force that results when one object makes contact with another and it's being pushed or pulled. It's the force we're normally going to push something with or pull something with. It's the action force. Tension force is a pulling force from a rope or a string on an object. It always points toward the rope or the string, so that's a pulling force. A rope, for example, would only be in tension. It's hard to push on a rope, so you can only have a rope being in tension. A normal force, this one's tricky, so put a little star beside that one. A perpendicular force exerted by a surface on an object in contact with the surface. So the normal force always points away from the surface. So if you have an object sitting here, the normal force is perpendicular to the surface. If you take that picture and we rotate it and we put that box on the side, the normal force stays perpendicular to the surface. Okay, that's a really important piece to understand about the normal force, and we'll see that in a few more examples. Frictional force, F of F, it opposes the sliding of the object across the surface. It always goes in the opposite direction of the motion. That's a real important piece. And a free body diagram, which is what we're going to draw on the next page, also sometimes called a force diagram. Okay, it's how we represent or show the forces acting on an object. And I'm going to warn you, please, 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 please watch the subscripts. They mean something. This little F capital N here for normal is going to be confused later on with something we call the net force, so please be aware of that. Okay, so drawing the free body diagram for the forces acting on the book that's at rest. So I'm just going to drag the forces I have over. So I'm going to put my normal force and I'm going to put my gravitational force. Okay, so it looks something like that. Because it's resting on the table, we should see that Fg and Fn, okay, are about the same size because the object is not moving up or down, so they have to cancel each other out and balance. If I'm sliding the book across the table, again, I have the same issue with the vertical direction, that Fg and Fn are going to be about the same magnitude. Okay, and then when I look at the frictional force though, and I look at the applied force, if I put them close to each other, let's see if I can get them close to each other, come on. We should see right away that the applied force has to be greater than the frictional force for this to move. And we'll have a long conversation about frictional force in the near future, but for now, those are my force vectors in a free body diagram. And as though this looks really, really simple, this is probably the most important element of doing force questions, is being able to draw this picture, because this picture tells you exactly what to do with calculations. Okay? We won't be doing too many of these ramps or two-dimensional styles of problems in grade 11, but we will see them in grade 12. But let's just have a quick look. What would the free body diagram look like for a book resting, so that's not moving, on a ramp? So there's a couple forces we have to look at. The first one is gravity. Come on, gravity, there you are. Okay, so this is Fg. And it's pulling down, it's straight down, it doesn't care about the ramp, it's always straight down. We also have a normal force, and you'll notice it's perpendicular to the surface. So the ramp and the normal force are at 90 degrees to each other. And then because this is resting, okay, then we need to have some sort of force that's keeping it from sliding down the ramp. So where we go with this in the future, if I break up f of g into components, you can see there is a component that matches the normal force. There is this unbalanced piece down here. Okay, and if I had no friction on this ramp, then that is the force that would bring the object down the ramp. But because there is a frictional force, I know the frictional force has to be at least as big as that so that it doesn't roll down the hill or slide down the ramp. Okay? If the book is going to start sliding down the ramp, there must be an unbalanced force in the system, and that's the one we just talked about. So if this was to slide, then what I would have to do is I would have to make my normal or my frictional force a lot smaller, and then I could see that this force down here that I got from gravity, it's bigger than the frictional force. The object would want to move down the ramp. Okay, the net force is the sum of all the forces acting on an object. This is the one that gets confused with the normal force, so please, please, please take your time on this. Net is not the same as normal. Net means we're going to sum them all up. Okay, so when we sum up our forces, we are going to usually use just left to right and up and down, our traditional axes that we use in positive convention. So normally this is what we're going to use. It is not the only way to do a problem, but it's what most people default to because it's common and familiar. So if we look at the ball on the side here, I have a 10 Newton force going to the right, 6 Newton going to the left. Okay, so when I set them up in my little expression, the net force will be 10 minus 6. So I'll have 4 newtons, and that means this 4 newtons is going to the right. So the ball, or the object, it doesn't really know that there's a 10 and a 6. All it really knows is that there's 4 newtons going to the right. Okay, so please, again, I'm going to repeat this. The normal and the net forces are completely different things. Please don't change those notations, those subscripts. Okay, the net force on an object is what the object feels. I just mentioned that. The object doesn't know how many forces are acting on it. It just knows what the net or the total force is. So when you look at this shape here, I've got a whole bunch of forces acting on it. So what is the net force on it? Well, if we look in the left to right direction, the horizontal direction, I've got 11 newtons going to the right, 6 newtons going to the left. The object only feels 5 newtons to the right. Okay, if I look in the vertical direction, I've got 9 newtons going upwards, 7 newtons going downwards. It only feels 2 newtons going upwards. And that's where the end of grade 11 is. Grade 12, though, we can look at some other stuff. And I'll just give you the quick highlight of where that may go. And then you won't see anything totally new here. But could I get a resultant force of this, just like we did in the motion section? Could I take the 2 newtons up, the 5 newtons to the right, create a little triangle, and find a resultant right here, and a direction of motion, or a direction of the resultant force? Okay, and that would be it right there. So the resultant would be 5.4, and this little angle in here would be 21.8 degrees. So we could handle that right now, but we leave most of those types of problems for grade 12. Okay, so find the net force acting on the 5 kilogram book resting on the table. So if you want to pause here and give this a shot. Okay, so hopefully you've had a chance to try it. So the first thing I want to do, and I want to get into a habit of this, is I want to draw the free body diagram. Okay, so there is an FG pulling down. It's resting. So that means the normal force going up should be the exact same magnitude as Fg. Okay. Determine the force of gravity. We just did that calculation earlier, so we know that's mass times gravity. So if I put in the numbers, I have a 5 kilogram book. Let's use the proper 9.8. And I think that's what, 49. Just to be safe, I'll double check because I had some silly errors the other day. 49 newtons. Okay, so determine the normal force. Okay, so the normal force, because this object is resting, that means the net force has to be 0. That these have to be balanced, otherwise the book would be either flying off the table or flying through the table. So the normal force has to be 49 newtons as well. Now we haven't put any directions on this, so if I wanted to add some directions, I could either say down, that would be one option, and this would be up, or I could use positive and negatives. That's another option. Okay, I'm going to say pause and try these. Okay, there's a bunch of questions here, so it'll take you a few minutes, and then I'll quickly go over some of the highlights. Okay, so the first question is calculate the net force when each set of forces acts on the same object. So we've got 5.5 west, you've got a 5.5 west, a 3.4 west, and a 4.2 to the east. So you'll notice those are all in the same direction. So when you add them all up, you'll be adding 2 of them together and subtracting the other one. We should get 4.7 newtons to the west. The rest are the same, so 92 up, 35 down, and 24 up. So again, you'd have 2 positives and 1 negative. By the time you add them up, you should end up with 33 up. And then lastly, for this question, you have 15 up, 15 down, so those 2 are going to cancel each other out. And in grade 11, you should notice that you shouldn't end up with too many that have forces in a vertical direction and a horizontal direction. That shouldn't happen in grade 11. Grade 12, yes, but not grade 11. Okay, so then when we get to 35 newtons east, 12 newtons west, we should end up with 23 to the east. Okay, a chain exerts a force of 1200 newtons up. So if we have some little box and we have 1200 newtons up, it experiences a force of gravity of 1100 newtons down. Okay, what is the free body diagram? Well, there it is. Okay, and what would be the net force? So the net force would be 1,200 minus 1,100 would be 100 newtons up. Okay? Come on, pen, keep rolling. There we are. And lastly, you push a book across the table to your friend with a force of 6.5 newtons to the east. The force of friction on the book is 4.5 newtons to the west, so you'll notice it's opposing the motion. So if we draw a quick free body diagram, we have a 6.5 newtons to the east. We have a 4.5 newtons as friction to the west. We already know the normal force and the gravitational force are going to balance because it stays on the table. If those are out of balance, the book would be, again, leaping off the table or falling through it. So the net force on this object should be 2 newtons to the right, or in this case to the east. And that would be our answer. Okay? And just throwing this out there, there are 4 main types of forces in the physics world. As you proceed and stay in physics a little longer, you'll encounter more of them. Our focus right now is just introducing this guy. We'll leave the other 3 for next year mostly. And here's a couple questions to try. So section 3.1, number 25715. You can try more if you like. Thanks for listening.